Hello, my name is Mike Avery from Cadence Design Systems, and in this video I'll talk about deferred immediate assertions and how the extra definitions have appeared during the evolution of the language reference manual. So here's a design we're going to be looking at and evaluating. We've got a clock, we have a logic signal K which gets set to 0 at reset and then inverted on every POS clock. And what we have here is a couple of combinational blocks. So in this combinational block, K gets assigned to J, and then J gets assigned to L. As you can see, when the POS clock arrives, K is inverted and this creates this cascade of combinational assignments. And ultimately we can, just from looking at the code, tell that L, K and J are effectively going to be the same value at any given time we choose to look at it. And this is borne out by a simulation. If we simulate this code, this is what we see: K, J and L having the same value and inverting on every POS clock. So there's no surprises so far. Now what you've also have noticed in here is we have a concurrent assertion. So those of you familiar with SVA will probably recognize this thing here, which is a concurrent assertion, and this thing here, which is an immediate assertion. The difference between the two is that, well, firstly, the way in which you can tell the difference between a concurrent assertion and an immediate assertion is that the concurrent assertion has this keyword property here and an immediate assertion does not. This particular kind of immediate assertion here is only allowable in procedural code. However, this concurrent assertion, I could equally copy this, paste it there, and that would be valid syntax, and it would actually behave the same as it would before I copied it and pasted it. So I'll just get rid of this again. Now the form of the immediate assertion looks exactly the same as the concurrent assertion. So you'll notice the expression we're evaluating is K equals L, a boolean, and the same is true for this immediate assertion here. For immediate assertions, this expression can only ever be a boolean. It cannot be a sequence or have implication in it and all these other things that we can use in concurrent assertions. So the syntax of this is we have an optional label here. It's always best to give labels, otherwise the tool will name this for you and it will be a meaningless name. Then colon, then assert. This could equally be a cover or an assume instead as well. For the purposes of this in simulation we'll use assert. And then we have the expression we're evaluating, and then if the assertion fails we have this else clause and we go and execute some procedural statement. In this case we're just using $display. You can go and do whatever else you'd like there. So the reason it's called an immediate assertion is because you evaluate this immediately, i.e. when you reach this line of code you evaluate that assertion with whatever values of K and L you have right now in the region in which you're evaluating that assertion. With a concurrent assertion that's different. When you say at POS clock, you're evaluating this expression only at every POS clock, and the values of K and L you're using are what's known as the preponed values, the value before the clock arrived. Okay, so remember it's the clock that is causing K to change and this cascade of combinational assignments. So when you're actually sampling at POS clock, you're looking at the value before the clock changed. So you're expecting this to always pass, this one here. However, for this one we don't really know what to expect because we're saying K equals L, but J has not been updated yet when we're evaluating this line of code here, this immediate assertion. And because J's not been updated, then we haven't forced an update to L either. So will this pass, will it not? Well, let's take a look. Well, we can see at these points here, this red circle with a white cross in it indicates a failure. So I'm failing at every time I'm evaluating that property. And we might guess the reason for this is because, you know, the signals haven't settled down yet. We're just doing iterations of regions of execution in the system Verilog execution model. So shouldn't really be surprised if that fails. So the next question is, well, that's not the result I want, because I can see that in a real design J, K and L are always going to have the same value. So how do I work around this? What we can do is use something known as a deferred immediate assertion. So this assertion we were talking about here, this is what's known as a simple immediate assertion. Simple immediate assertions can only exist in procedural code. I could not copy and paste this outside of procedural code, so I couldn't cut it from here and paste it down here, for example. That would be a syntax error. Here we have a deferred immediate assertion, and you can see the difference between the two. If I line up this text, so it's easier to tell now that it's #0. This form of the immediate assertion is valid in the 2005 Language Reference Manual for System Verilog. That's the IEEE Standard 1800. In 2009 they added this #0. That's a deferred immediate assertion, and what it does is it delays the evaluation of that assertion until a later region in the current time step. So what do we mean by regions in a time step? So we're looking at the latest IEEE standard for System Verilog, which is the 2017 standard, IEEE Standard 1800 2017. And if we were to look at the execution model of hardware, this is what we see. So if we zoom out to see the whole diagram, because it's quite big, you can see all these different regions here. So this represents a time slot. So this is the same simulation time. All these things happen at the same simulation time. So only when we advance to the next time slot, as shown by this arrow down here, are we advancing time in simulation. So you can see several regions. One that's interesting to us as far as concurrent assertions go is this postponed region. So we're sampling the values of signals with which we start evaluating assertions with. But it's not until later in this time slot that we start actually evaluating the assertion itself. So for deferred assertions, we are evaluating them in this observed region here. So that's once all these non-blocking assignments have occurred. Now at this stage, all these signals should be stable at this given time step, but it's still possible, however, via other mechanisms like, for example, PLI, to go back and re-evaluate the non-blocking and blocking assignments. Now, another region we're going to talk about in a minute, so I'll mention it while we're looking at this diagram, is this postponed region here. So this postponed region, by the time we reach here, there is no possibility for any more signals ever changing again ever via whatever mechanism you choose. So nothing will work. Nothing can update signals from now on. They're all kind of non-writable, including PLI or any other thing you wish to connect to your simulator. So at this point, we know the signals will never change again at the same simulation time. So let's go back to our code. This final one here. This is still an immediate assertion and a deferred one, but it's known as a final deferred immediate assertion. So the keyword final here is the difference between the two being this final and this other thing, which is still a deferred. So for this one here with a #0, assertions are evaluated in the observed region. For final, this assertion is evaluated in that postponed region that we saw, i.e. we know signals will never change again at the current simulation time. Here, it is possible the signals could change again at the same simulation time via mechanisms like PLI, for example. So this particular simulation, if we were to show, what do we observe as a result, we can see that these deferred assertions are actually passing as we might hope. That's the whole intention of using these deferred assertions. I don't care about all these glitches in the combinational signals during any given time step. And even that, given this code, it may or may not depend upon the order in which the code's written, the order in which the simulator decides to evaluate the always blocks and so on. I might end up with a different result with the immediate assertion, but not with these deferred assertions. Another thing you have to be careful of is this final keyword only exists here as used in immediate assertions from the 2012 standard onwards. So that's the 2012 standard and 2017 standard. You can use this. Now another interesting thing is that when you do this, if I copy these out, because these are deferred assertions, I can paste these outside of procedural code and that's still valid to do that. So there's a special name in the language reference manual for these things. So collectively such things are known as common module items. In this specific case, these are known as static deferred assertions. Remember, I couldn't do the same thing with this immediate assertion. It will be illegal to paste that outside of procedural code, but with these deferred immediate assertions, it's perfectly okay to do that. Okay, so just to summarize the main features then, immediate assertions can go in procedural code. The difference between them and concurrent assertions is you don't have a keyword property here. So if I were to type, for example, that, this line now becomes a concurrent assertion. If I delete that, then it's back to being an immediate assertion. Both are valid syntax. This form of simple immediate assertion can only be used inside of procedural code, not outside of it. This form here, deferred immediate assertion, you either have #0 or final, and that dictates in which region does the assertion get evaluated, which region in the current time step that is to say. And that concludes the explanation of what deferred assertions are. So thanks for listening. I hope you found that useful, and goodbye.